In the last session, we finished by talking about the probability waves that de Broglie discussed when considering matter. What he said was that matter shows wave-particle duality, and a probability wave is the best way of describing that. It doesn't mean that the lump of matter, i.e. something with mass, actually is a wave. It's a reference to the idea of locating it, the probability of where you will find it, which in itself is a very bizarre idea and in some ways is very difficult to make sense of. At the end of the last session, we discussed this with respect to the probability waves that were drawn, as we see in the diagram here. There are three wave functions that are drawn, the top three, and they produce probability functions which are shown below. The end of the last session had a discussion about this first wave function and its probability function, and how it just doesn't seem to make sense. It discussed the idea that if we consider an oxygen molecule, and we consider an oxygen molecule as one particle in what's called an ideal gas, then the probability function, the idea of trying to work out where will I find the object in a room, for example, just doesn't match with this probability function. As we saw last time, the probability function in that case would be this given here. In other words, as the oxygen molecule bounces backwards and forwards, and we considered one-dimensional motion just to keep it simple, because it's traveling at constant speed because there are no forces acting on it, it will not be accelerating, which means it is likely equally to be anywhere. Now, the alternative was the idea of trying to imagine something oscillating backwards and forwards between two walls and describing it using simple harmonic motion. But then again, we end up with a probability function that just doesn't seem to agree with de Broglie. So, having considered the first probability function, what about this second one? If we look at this wave function here, it produces a probability function which is symmetric about the center point of this one-dimensional motion. The room would essentially be mixed into two halves. On the one half, it would be most likely to be found in the middle, and on the other half of the room, it would be most likely to be found in the middle. But the weird thing is that if we put a detector in the middle of the room here, then sometimes you would find the object on the one side of the room. At other times you would find the object on the other side of the room, but you would never detect it going through the middle. And that just seems inconceivable. How can it go from one side of the room to the other along the only path that's allowed, but it cannot be detected at a certain point? This simply doesn't make sense. And that's because most people will be thinking of the oxygen molecule as a particle. And obviously, if it's in one location and then moves through a distance to another location, it traveled through all the points between those two locations. However, when it's considered to be a wave, this is entirely possible. Imagine two people with a slinky strung between them, and the one person oscillates their slinky with a pulse of energy that makes the slinky do that, and that pulse will travel along the slinky, and the other person at the same time generates a pulse going in the opposite direction of this type. Now, as these two pulses meet in the middle, the one pulse will be trying to make the slinky move downwards. The other pulse will be trying to make the slinky move upwards. So as these two pulses overlap, they cancel each other out. So the one half of the slinky will experience the motion of the pulses, as will the other half. But in the middle, where they cancel out, there will be nothing detected, no movement of the slinky whatsoever. That is essentially what is happening here. When we talk about the wave nature of an object, and we talk about the fact that the wave function can generate a probability wave, we're not talking about a single wave. The probability function is created by a combination of waves that produce its shape. And like waves or wave pulses on a slinky, that can produce points where cancellation occurs and we get zero probability. Again, a really bizarre way of thinking about particles. Now obviously with this idea of drawing wave functions that must have zeros at the ends, like we see here and here, like we saw with the first wave that looks like that, and the second wave that we've drawn above, and the third wave that looks like that, there's effectively an infinite number of them. I can keep drawing an infinite number. If I look at this wave shape here, then I can see that that is half a wavelength. If that's not entirely obvious, then consider the following. An imaginary x-axis, a sinusoidal variation. Now, if we're trying to draw from a 0 to a 0, in de Broglie's idea, the walls, the confining edges, have to have a wave function with a value of 0 so that when you square it, the probability stays at 0. Then I can see that the first 0 is there and the second 0 is there, which is why the first wave shape that's allowed looks like that. Now you can see quite clearly, I think, that that is half a wavelength, because one whole wavelength, one cycle, is that. And this is half a cycle. If we draw the second wave function that's allowed, we're going from a first 0 to the third 0 along. That's one whole wavelength. If we go to the next 0, that's 1.5 wavelengths. Each time we had an extra one of these sort of lobes, we're adding an extra half a wavelength. So when we look at the allowed waves, the waves that can fit between the confining spaces, we're basically increasing the number of half wavelengths by one each time. The first one is 1/2 wavelength, second one is 2/2 wavelengths, which is the green one here, third one is 3/2 wavelengths, etc., etc. There are an infinite number of wave functions that can be drawn. Okay, so let's get back to this idea of, does this in any way make sense? We've already seen that the probability function doesn't really seem to make logical sense. So let's consider another way of looking at this. Let's imagine that we take de Broglie at his word. We assume that you can represent an object with mass as a wave. So consider a person moving through a doorway. Let's assume that actually we've removed the door from its hinges, so it's just a gap. And we're going to have a little person walking through the doorway. Now when a person walks through this doorway, if the person can be represented as a wave, then that would be equivalent to a wave moving through a gap. And that's what we see when we have diffraction. So this situation leads us to the idea that we can consider basically a wave moving through a gap, and you get what's known as diffraction. Now diffraction is the spreading out of a wave as it goes past an edge or through a gap. A gap, I guess, is just two edges. And we have an equation that describes this process. If we consider the wave to be, let's say, a light wave, then if there was no such thing as diffraction, and you basically imagine that you have a gap, you shine light through it, and the light falls onto a screen. If this was in a lab, the screen could be, let's say, the whiteboard at the front of the class. Then if there was no such thing as diffraction, if light travelled in this straight line and did not spread out at an edge, then if we drew an intensity pattern, we might imagine that it might look like this. On the screen there would be no intensity, and then we would suddenly get a sharp bright patch on the screen, effectively representing the size and shape of the gap. No diffraction. However, if the wave spreads out at the edge of the gap, you might imagine that some of the energy gets spread to the side, So you lose a little bit of your energy to the sides. In the middle, in this region here, you would assume that because this is not touching the edge, that there's no effect here. It's only at the edges. So you might imagine that the intensity is the same in the middle, but then at the edges it gets spread out. So you get this kind of effect. And that would be with some diffraction, some spreading out. Now it turns out that when you actually do this experiment and you shine light through a gap, neither of these is what you get. Light does diffract, but it doesn't spread out in a nice simple way like the green one suggests. What actually happens is seen by imagining a center line. You get a spreading out that looks like this. And that looks really strange, because right in the middle you get a peak, but just to the left and to the right of it the intensity falls, even though the light was passing straight through there. So diffraction itself is quite an interesting effect, never mind de Broglie and his idea about waves. But we have an equation that connects the red pattern of diffraction, and it basically is an equation that tells us about the angular spread of these peaks that we see. Remember, this is an intensity pattern, if you like, brightness on the screen. And the equation tells us about the positions in angle of the zeros. So we have a 0 there, and we have a 0 there, and we have a 0 there, and we have a 0 there. We number them. We give them a letter n. N equals 1, n equals 1, n equals 2, n equals 2, etc., etc. What actually happens if we go further and further into larger and larger angles is that we have a central peak, but then the peaks get smaller, smaller, and smaller as they fade out. And the pattern is symmetric, so this pattern will be reflected on the other side of the center as well, which is why we get 2n equal 1s, 2n equal 2s, etc., etc. There's a beautiful symmetry about this. So imagine we had the center of the gap and we drew a straight line to the zeros. The angle to the dotted center line is what we call theta 1. The angle from the center to the second 0, that's what we would call theta 2. And there's an equation that gives us the so-called angular position of the zeros. N lambda is a sine theta n. For n equals 1, that means lambda is a sine of the angle about the center line to the first 0. Now, if the red pattern were, for example, linked to a probability function, then that would mean that when the wave travels through, which is equivalent to the person moving through in the example that we're using, it would suggest that the probability of where they arrive when they get on the other side of the door is not clear. It could well be that the person walks through the doorway and ends up most probably in the middle here. However, there is a probability that they will appear on the other side of the doorway to the side, or maybe even at a much bigger angle. Now, this seems frankly ridiculous. And this does raise the issue of free will. When I stand on one side of a doorway and the doorway is open, and I wish to walk through the doorway onto the other side, I feel that I am making the decision about how I walk through, when I walk through, and where I will be when I arrive on the other side of the doorway. However, this is suggesting that I don't have that power. Basically, physics will decide. When I walk through the doorway, if I'm behaving with a wave nature that determines where I can be located, it suggests that when I walk through the doorway, physics will determine where I end up on the other side. I might end up to the side, all the way over here, and that just feels really weird. Nobody likes that idea because it removes the concept of free will, or at least it means that we have to redefine free will as being something different. So let's work this out then. We have the equation for the angles for diffraction. So let's put some numbers onto this. And let's try and choose sensible numbers that make sense in the real world. So the question, do we see a person diffract when they move through a doorway? So the situation that I'm going to imagine is I have a doorway, and the doorway I'm going to assume, to keep the numbers nice, is 1 meter wide. Now 1 meter is a little bit big for a doorway. Most house doorways are a little bit smaller than that. But in a lab, a 1 meter wide doorway is not outrageous at all. I have a person, and the person is going to walk through the doorway. I'll give them a speed, 1 meter per second. 1 meter per second is not an outrageous speed, it is a reasonable speed. Mass. The average mass of a person on Earth is apparently somewhere around 72 to 73 kilograms. I'm going to choose 66.3 kilograms. 66.3 is not 72 or 73, but it's pretty close, so it feels like a reasonable mass. The equation that describes the angular positions of the diffraction pattern, which is going to give us basically the probability function, is n lambda is a sine theta n. And we're just going to consider the first order, n equals 1. So again, that equation becomes lambda is a sine theta n. What I'd like to do is imagine that we can describe this person as a wave and work out what the value of theta 1 is. Now, when we describe the person as a wave, we need to use de Broglie's relationship. De Broglie told us that the wavelength of matter is given by h over p, which is h over mv, the momentum. H is Planck's constant. So I can rewrite this equation by basically mixing these two equations together. H over mv is equal to a sine theta n. Therefore, h over mav. And now I can put the numbers in. H is Planck's constant, 6.63 times 10 to the minus 34. The mass is 66.3. So now you can probably see why I chose 66.3. Planck's constant is 6.63. And now note, please, 6.63 is the same as 66.3 times 10 to the minus 1. Which means I can change the top number here, and instead of having 6.63 times 10 to the minus 34, I can change it to 66.3, just to make it really obvious, times 10 to the minus 35. Times by A. A is the width of the slip, which in this case is 1 meter, times by the velocity or the speed. The difference between velocity and speed is not really important in this case, of 1. So I end up with sine theta 1 is equal to 10 to the minus 35. This means that theta 1 is sine to the minus 1 of 10 to the minus 35. If that's put into a scientific calculator, we get 6 times 10 to the minus 34 of a degree. Now, frankly, that's way too small for a human being to ever judge. What we're basically saying is when a person walks through a doorway, a typical person through a slightly large but not untypical doorway, they will diffract. It means that they will appear potentially to the side. and their spreading out in their probability function is over an angle each side of the center line of 6 times 10 to the minus 34 a degree, an angle which is way too small to ever be seen or detected. Now, of course, the probability function has a bunch of peaks, but the point is they die away, and they die away very quickly. This would be n equals 1, this would be n equals 2, that would be an angle like that, n equals 3, but as they die away, they become less and less probable. And the largest value of n that you could reasonably assume you might conceivably be able to experience is around maybe 5. So that's not going to have much of an effect on such a tiny number. It is still going to be a tiny, tiny, tiny number. So what we seem to be seeing is that diffraction may happen, but it is far too small an effect to ever be seen. Which feels like a bit of a get out. It feels like a bit of a fiddle. Oh, you say it happens, but you can't detect it. So let's just, before we give up on the idea that this feels like rubbish, we can't detect it, so maybe it is rubbish, let's just look at why this value is so small. The equation for sine theta is h over MAV. Now, the reason that sine theta is so small, and so theta is so small, is because Planck's constant is so small. The number on the top of this equation is 6.63 times 10 to the minus 34. That is such a small number. If we want the angle to be something significant, like, say, 10 degrees, then we need sine theta to be much bigger, which means we need h over MAV to be much bigger. There's nothing we can do about Planck's constant. Planck's constant is what it is. But in order to make this ratio bigger, it means that we need to make the numbers on the bottom smaller. We have the mass of the object. A human being is just too heavy to see these effects. So let's go for an object that has a very small mass. The object that has the smallest mass that is very, very easily available is an electron. Second thing is the size of the gap that the object's moving through. That's A. The smallest easily convenient distance for an electron would be for it to shoot through the gap between atoms. If we look at the arrangement of atoms in a solid, the gap between them is about the smallest that typically an electron could have as a gap to move through, and that's going to be about the size of an atom. So if we use electrons fired at a thin film, we could potentially then maybe try and get something that seems a bit more reasonable. So what we're going to do is consider the idea that the mass is the mass of an electron, and the mass of an electron is 9.11 times 10 to the minus 31 of a kilogram, much, much smaller. The size, A, will be passed between atoms, so it's about the size of an atom, and that's going to be around 10 to the minus 10 of a meter, a so-called angstrom. Now, I don't know what velocity an electron would need to have, so let's just change the scenario slightly. Let's imagine that we've got a bunch of atoms and an electron is going to pass through the gap between them with a velocity v. Now, electrons are like tiny little lumps of matter, a particle, but we're talking about de Broglie describing them as having a wave nature. So we remember again that the wavelength is given by h over mv. And we want diffraction to be of a reasonable amount. So let's suppose that we want a diffraction angle of something that we could probably detect with our eyes. 20 degrees. I could easily imagine 20 degrees. So what we want is theta 1 to be equal to 20 degrees. The equation for the angular position is given by n lambda is A sine theta n. We'll do it for n equals 1, and we'll make the angle theta 1 equal 20 degrees. So now we have h over mv is equal to A sine theta 1. And now we can put the numbers in. 6.63 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31 times by v is equal to 10 to the minus 10, the size between the atoms, times the sine of 20 degrees. Now this allows us to work out the speed that the electrons would need to have in order to produce a 20-degree angle. So that means V is equal to 6.63 times 10 to the minus 34 over 9.11 times 10 to the minus 31 times 10 to the minus 10 times by the sine of 20. And that works out to be 2.1 times 10 to the 7 meters per second, which is about 7% of the speed of light. Now, I don't know whether that's a sensible speed or not. If it was above the speed of light, then I would definitely say not sensible. But I don't know whether that speed is sensible. So let's do something that physicists often do. Every time we do a calculation in physics, what we should try to do is ask ourselves, does this number make sense? So let's ask ourselves, does this number make sense? Does a speed of 2.1 times 10 to the 7 make sense? Is it easily available to get to that speed? Or is that some crazy speed that is way, way, way too high and it's just practically not possible? The easiest way to answer that question is to convert the speed into something that we can make sense of. Let's imagine that we accelerate an electron with an electric field to get it to this speed. That's a speed of 2.1 times 10 to the 7 meters per second. The question is, what voltage would we need to do that? So the idea is that we have two plates. We have an electron. We have a voltage between those two plates. And we're interested in what voltage we would need in order to get the electron so it has that speed when it reaches the other plate. Now, the kinetic energy gained by a charged object when it moves through a voltage V is given by QV. Q is the charge of the object, V is the voltage that it has moved through. That's the kinetic energy, which of course is a half mv squared. Now we know what the speed is, V, that we want. And we know the mass and we know the charge of an electron. So we should be able to work this out. Basically going to set QV equal to a half mv squared. So we need the voltage. So we rearrange this equation for voltage, which is mv squared over 2q. So the voltage needed is going to be given by 9.11 times 10 to the minus 31 times by 2.1 times 10 to the 7 squared divided by 2 times by the charge of an electron. And the charge of an electron is 1.6 times 10 to the minus 19 of a coulomb. So that gives a voltage required of 1.3 times 10 to the 3 volts. And that's 1300 volts, just over 1 kilovolt. Now, again, does that number make sense? Is that a reasonable number, or is that a stupidly high number that could not practically be reached? And the answer is, this is fine. In typical labs, you're not going to get that kind of voltage from a battery, but any A-level physics lab that does experiments on capacitors, for example, might easily have a power supply that goes up to 5,000 volts. So to get 1,000 volts is not a big deal at all. So this is possible. We could literally get a situation where we have electrons accelerated by around 1,000 volts. This would give them a wavelength which, when they went between the atoms in a thin film of a solid, would produce a diffraction pattern. that would actually only be described using the idea that the electron had a wave nature. If you look in the earlier video posts, you'll see a discussion about what we refer to as wave effects and particle effects. And diffraction is a wave effect. Diffraction can only be explained using the concept that the thing that you're looking at has a wave nature. And electron diffraction seems to be something that we are predicting could happen and should happen if truly a lump of mass can be viewed as having a wave nature. And if I just show this web page, you will see here that actually electron diffraction is a common technique which is now used by scientists, predominantly physicists, to look at the structure of materials. And so de Broglie went from a position where basically people didn't really believe what he was saying to being able to, through his theory, predict electron diffraction. Note that in 1927 there was experimental confirmation that matter waves existed when Davison and Germer produced electron diffraction. This is now an accepted technique. Experimental confirmation was actually not what they were aiming to do. They were not trying to confirm de Broglie's hypothesis. Their confirmation of de Broglie's work was a byproduct basically of their routine experimental studies of metal surfaces under electron bombardment. So it was a bit of a fluke. But again, it falls back on this idea that in physics we're trying to look at the universe. We're taking every piece of experimental evidence to try to help us understand the rules of the universe. Okay, so de Broglie's idea has been experimentally confirmed. Does that mean it's correct? No, it doesn't. Just because something is experimentally shown does not mean that the idea is correct. The way that we discuss it in physics is we say that the Davison and Germer experiments supported the idea that electrons may have a wave nature as well as a particle nature. It is now well established that wave-particle duality exists both for electromagnetic radiation, which is normally considered as a wave, and for lumps of matter, which is normally considered as a collection of particles. Wave-particle duality is not a particularly pleasant idea because it introduces some very strange ideas that don't seem to make logical sense. However, it is the only explanation that we have for a whole array of observations associated with atoms, molecules, subatomic particles, etc., etc. And in the next session, we will move on to look at what wave-particle duality actually means for us, and in particular, how wave-particle duality leads to what's known as energy quantization. But until then, be happy, take care, and I'll see you next time.